USB drive left in there.
I've seen a lot of tech left behind this one.
Yeah?
Yeah.
Maybe it's alien abduction. Find people who are tech savvy and take them away. That's
We
what I'll
need-
ditch.
We need new IT people.
Yes. All right. Any questions from yesterday? We got as far as the sum rule. Sorry, the product rule.
Seems easy so far, so.
It is
I'm
easy
waiting
so
for-
far.
I'm waiting for the twist.
No, there's no real twist, but we can use it in some twisted ways.
That would make it a twist.
Yeah. So, how many ways can you order a deck of 52 cards?
Isn't
52
it,
factorial.
Yeah, 52 factorial.
Why?
I know, is
Because
it
that's how-
exactly 52 factorial? I thought it was a slight twist on that.
If it's a regular deck with 52 distinct cards, I think it's just 52 factorial.
Because if you look at each, obviously when you have any arranged
Share
cards,
card
you're going to have 52 slots.
Mhm.
So you figure out slot one, how many possibilities you have, 52, okay, the next one, how many possibilities you have, 52 minus 1, 1 cards.
Okay.
Second one, 52 minus 2, so on and so forth, until you get a number that is 52 factorial.
Cool. So it is the product rule again. We can think of arranging a deck of 52 cards as 52 tasks. The first task is to pick the first card at the top of the deck, and there's 52 ways to do that. The second task is to figure out which card's going to go right below that, and you've only got 51 cards left, so you got 51 ways to do that, and then 50, and so on. And that's where factorials come in handy. That's just the product for the first 52 integers.
That's a very big number, by the way.
It is a very big number. It doesn't blow up your calculator though. Like 79 factorial, I think, is the largest that most calculators do. Old school calculators. The ones that blow up at 10 to the 100.
So far, calculators here on factorial tables. Let's see if I can break
Well,
it.
you got a better calculator. So how many 3-digit numbers are there? And how do you answer the question using the product rule?
Oh, it's just,
The first would be 1,000? Yeah. No,
10 ways
that's-
to
that's
do this
right.
task, which is picking the first digit.
If you count 000,
Yeah,
then it's 1,000, otherwise it's 999.
yeah. If we allow any 3-digit number, including 000 or 002, it's 10 times 10 times 10, that's 1,000.
It all hinges on whether you count leading zeros or not.
Okay, let's look at 2-digit numbers.
Well, I mean, again, if you don't count the leading zeros, that puts you down to, like, what did you say? 89, I think it would be. That'd be like 89 right here. 'Cause
So,
you can't count the first 0, 1, 0, 2, 0, 3 unless you're counting the leading zeros. If you count the leading zeros, then you've got 99 right here.
well, going from 0 up to 99.
So
So
100.
we've got 100. If we don't allow leading zeros, how many ways can we complete the task of filling in this digit?
109, so 8. Because you can't use zeros.
1, 2, 3, 4, 5, 6, 7, 8, 9, that's 9.
Yeah, 9.
So 9 possible ways to fill that in.
But
And then for this digit, 10 possible ways, so we've got 90 possibilities.
But if we tack on another digit, then it's 9, 10, and 10.
Yeah, then it gets a little weirder, because you want to suppress the first two, and we'll get into the sum rule for that. So we have a function from a set M to a set N. These are finite sets, and the size of them is little m, little n, respectively. How many possible functions are there? How can you break this down to use the product rule? So what does f have to satisfy to be a function? What does it mean to be a function? Not necessarily.
We just have to be able to map them together.
We have to be able to map every element in M to some element in N. It has to be defined on all elements in M, because that's the domain. And it has to take each element to exactly one element. It can't take a particular M to more than one value. So if we wanted to construct a function, we need to specify what it maps each of the elements of M to. That's our procedure, and we can break it into a series of sequential tasks. Choose the first element in M, decide what it maps to. Choose the second element in M, decide what it maps to, and so on. And since these are finite, they're countable. So I'm going to say task 1. Choose what f of m1 equals. Task 2. Choose what f of m2 equals. All the way down to task. How many of these tasks do we have? We have m, because we have m elements in our set M. So down to task M. Choose what that last element maps to. And how many ways can we complete task 1? How many different things could we map this particular point to?
N times?
Oh, wait, no, we're not with one, so we can.
It can map to any of those n elements. So we have m tasks, each one can be done n ways. The total number of functions, let's see if we can get it right, n to m. But now, what if this is injective? How many ways can we complete task 1? That's still n. How many ways can we complete task 2? That's got to be n minus 1. Because we can't map to the same thing that we mapped here, so we've got one less n that we can map to. And this last one is something I don't want to write the expression for. But the total number of injective functions will be a product n times n minus 1 times n minus 2. A total of m of these terms. And we're going to see that kind of expression pop up a lot. Right, 52 cards, the total number of possible decks we can have is 52 factorial. But what if you're drawing a hand of 5 cards from a deck of 52? There's 5 tasks. Pick the first card, second card, third, fourth, and fifth. how many ways can we pick one card from a deck of 52?
52.
To pick the second card, we have 51 choices. So that's the total number of 5-card hands that we can draw from a deck of 52. Assuming we draw a card, we don't put it back in, we hold on to it. That's the number of combinations. And it's clearly smaller than 52 factorial because we're not multiplying by all these other things. But is there a nice succinct way you can think of to write this product using factorials?
Is it 52 factorial minus, say, 47 factorial?
Yeah, divided by. Right, that's a ratio of factorials. Because 52 factorial is this multiplied by 47, 46, 45, 44, 43. And if we divide by 47, 46, 45, 44, 43, we're left with just this. And we'll come back to that later today or maybe tomorrow. So for a finite set S, its power set, which is a collection of all subsets of S, we had a rule for the size of this, and it turns out to be 2 to however many elements we have in S. And we can prove this pretty easily using the power rule, product rule. To pick an element in the power set means to pick a subset. Right? The size of the power set is the number of possible subsets. So if we create a procedure to create a subset of S, how would you pick a subset of some set? You're on a desert island, you got a box of 50 objects, you want to make a subset of that set. How would you do it?
Grab one out.
Pick one out. That would be a subset of 1. Keep going.
Pick another.
Pick another one out. Pick this one out, throw it away. Pick this one out, throw it away. Pick this one out, keep it in your set. Go through your whole collection of 50 items, and the ones that you kept, that's a subset. In fact, the ones you threw out, that's another subset. So we can think of this as a series of tasks. Choose whether to keep the first element or not. Second task, choose to keep the second element or not. All the way down to choose whether to keep the nth element or not, where n is the size of the set S. And how many ways can we do each of these tasks?
S minus 1, S minus 2, S minus...
Well, each task, this task says we're either going to keep the first element or we're not going to keep the first element. We got 2 ways to do this. We can keep it or we can not keep it. We can keep the second one or not keep the second one. We can keep the third or not keep the third. Each of these can be done in 2 ways. product rule, total number of ways we can do the entire collection of tasks is the product of all of these, which is just 2 to the size of S. So that's the number of subsets we can form, and since the power set is the collection of all subsets, the number of things in the power set must be 2 to the magnitude S. And if we were to think of membership tables where we make a binary string, where each bit corresponds to an element of S, and a subset is just a string of 1s and 0s, this is just the number of possible binary strings of length magnitude S. So we've already done that before. All right, so let's look at the sum rule. If a procedure P can be done either by completing task T1 or task T2. So it's no longer a succession of tasks, it's an either or. And T1 can be done in one ways. And T2 can be done in 2 ways. And the total number of ways to do our original procedure is N1 plus N2. So you have 100 teachers and 25 students. And your procedure is to choose either a student or a teacher to go to some conference. You're going to pick one person. They can be either a teacher or a student. So P, send one person to a conference. And we can think of that as 2 possible tasks. T1, choose a teacher. T2, choose a student. And if we do either of those, then we've completed our procedure. So T1, send a teacher. T2, send a student. We can't do both because we're not allowed to send 2 people. But we can do either T1 or T2. So how many ways can we complete T1? There's 100 choices we can make. So there's 100 options. And if we decide instead to do T2 to send a student, there's 25 ways we can do that. So N1 plus N2 equals 125. That's the number of ways we can complete procedure P. Is this making sense?
Except for there's 100 teacher and only 25 students.
That is a little weird, isn't it? Maybe they're really difficult students. They're really bad teachers.
Or it's just eligible students and not every student is eligible.
That's possible.
It's a really big school.
Yeah.
I feel feel like maybe there's, well, maybe it could be college, large university or something.
Yeah.
All right, we made it reasonable, folks. Good
Teacher
job.
could be a euphemism for guards, and students could be prisoners. We're going to like a correctional conference. I used to work at this national lab, and after a number of years there and observing the people there, I came up with this theory that it was really an insane asylum, and we were all inmates, but we were inmates who were also kind of intelligent, and they wanted us to like do creative work, and so they told us that we worked for this lab. And I started noticing like the barbed wire around the facility, it was angled in a way to keep people in, not keep people out. And we had ID badges you had to show to security on the way in, but you also had to show your badge on the way out.
Wait, what was it?
It was a research lab.
That
But-
was yours.
Yeah, so they said,
Black Mesa?
so you never know.
Mesa.
All right, you're at a restaurant, and you can get super salad, and an entree, and a drink. And they have 3 kinds of soup, and 5 kinds of salad, and 4 entrees, and 7 drinks. So how many possible meals can you have?
The quantity 3 plus 5 times 4 times 7.
That was too quick. But you're correct.
Basic probability stuff.
Yeah. So we can think of this as a combination of product rule and sum rule. Right? In order to order a meal, you need to do the following. You need to choose super salad and which one you want. You need to choose an entree and you need to choose a drink. So this, let's call this T3, and let's call this T2. These are being done in succession. You're going to choose your entree, you're going to choose your drink. This is going to be done, let's say first, we're going to choose whether we want super salad, and based on that, which one we want. And we can break this into 2 subtasks, like T A and T B. And we accomplish this first task, T1, by doing either TA or TB. That's a sum rule.
It's like a struck.
Yeah. Because we got stuff inside stuff. So, task 1, we can do 3 plus 5 possible ways, where this is the number of ways to do TA, this is the number of ways to do TB. Task 2, we can accomplish 4, and task 3, we can accomplish 7 ways. And now we can use the product rule because we know we're going to accomplish our task by doing this and then this and this. And so our total number is, as Ian said, 3 plus 5 times 4 times 7. Whatever that is. 256 minus 32. 224. All right, I want to talk about subtraction.
I don't know, this company stuff is really complicated.
Yeah. All right, let me talk about subtraction. We had this when we did set theory. The number of elements in the union is the number of elements in each set minus the number of elements in common. Because if an element's in common, we're going to count it twice. Once in A and once in B, so we subtract that off. And this is basically the idea of the subtraction rule. So if we want to perform a procedure that involves either doing this task or this task, we can find a number of ways to do this and a number of ways to do this, but if it's possible that we could be doing both tasks, we need to subtract off the number of ways that we can do both tasks together. And so let me just give you an example of this. Suppose we have an 8-bit number, so our procedure, pick an 8-bit number, begins with a 1, and it ends with a 0, 0. Sorry, 4. So we want to find the number of 8-bit numbers that begin with a 1 or end with 2 zeros. And here's what we can do. How many 8-bit numbers begin with a 1?
2 to the 7?
2 to the 7th. So we have 128 possibilities there. If we end with a 0, 0, how many numbers are there?
6.
2 to the 6th. So the total number of things that begin with 1 or end with 0, 0, we'd be tempted to say it's 128 plus 64, but it's not. Because,
You need to account for the middle. don't you?
yeah, there's double counting. There's numbers we counted in here that end with 0, 0. And there's numbers we counted in here that begin with a 1.
2 to the 5.
So, yes, that's the answer if you're answering the question I'm about to ask. So how many numbers are in the overlap between these two sets?
2 to the 5.
Right, so begin with 1 and end with 0, 0. That's 1, followed by any 5 digits, followed by 0, 0. There's 32 of those. So you have to subtract 32 off of this sum of these sets. And so 128 plus 32 is 160. And it's got a fancy name. Principle of inclusion, exclusion. All right, let's talk about pigeonholes. Pigeonhole principle. Do you know what pigeonholes are? You have like a wooden box and there's dividers in there and pigeons sit inside each box. So if you like,
I think I remember
yeah. So if you send messages by pigeon, right, you train your pigeons and they usually sleep outside, so you have this box. And if you got 25 pigeons, you got 25 holes and they hang out in there and sleep and stuff, and then they carry messages and so on. People used to actually use this for sending information. It was good in times of war in particular, because pigeons can go where people people can't. So, if k is a positive integer, and k plus 1 or more objects are placed in k containers, then at least one container has 2 or more objects in it. So picture your crate with 25 compartments in it. If you have 26 pigeons who are going to occupy those containers, at least one of those containers is going to have 2 pigeons. Because you've only got 25 holes, you got 26 pigeons. You can't fit them all into holes unless at least one has 2. So here's 3 boxes. Here's 3 letters. I can put 1 letter in each box. And when I'm done, each box has no more than 1 thing. I could also put my letters in boxes like that, and I've got 2 objects in that 1 box. But if I only have 3 of these and I have 3 holes, it's possible for me to do this. What the pigeonhole principle is saying is if you have 4 letters, there's no way I can put them into these 3 holes without one of these holes having at least 2 letters in it. Does that make sense? I mean, it's a pretty obvious principle.
Yeah, exactly. I don't get what it tells us though.
It tells us all kinds of things. For example, you're in a room with 8 people, and you're talking about your birthdays, and what day of the week you were born on.
Oh.
Guaranteed at least 2 people in that room were born on the same day of the week.
Assuming you have more than 7 people.
You got 8 people,
8 people, 7 days a week.
right? And that's the pigeonhole principle. You can think of the day of the week that you were born as being a bin, and you've got 7 possible bins. You can put somebody in based on the day of the week they were born. You've got 8 people in 7 bins. One of those bins will have at least 2 people in it, which means those 2 people were born on the same day. So that's the pigeonhole principle.
Just chuck people in the day of the week then.
You're a Tuesday person.
There's a poem that talks about that.
Is there? Oh yeah, Monday's trying, yeah.
Yeah.
If you have 27 people in a room, at least 2 of them have the same first initial.
D.
Yeah. Right, and then if you think about it for a pretty short amount of time, it's pretty obvious that that's true. But you can actually prove it by invoking the pigeonhole principle. If you have a 10-point quiz and you have 11 people in the class, at least 2 people got the same grade. Well, 12 people, because your grade could go from 0 to 10. So there's 11 possible grades. If you got 12 people, at least 2 people got the same grade. Now it could be everybody got the same grade, everybody got 10 out of 10, or it could be half the people got 10 and half the people got 7. The only thing the pigeonhole principle is saying is it's not possible that each person got a different grade from everybody else. There has to be an overlap if you have, in this case, 12 or more people. And you can generalize this. If you have 15 people in the room, at least 2 of them have to have been born on the same day of the week. If you have 22 people in a room, at least 3 of them had to be born on the same day of the week. So there's a generalized principle. Which is where you have n objects and k boxes. And at least one box has to introduce some symbology that I haven't introduced previously. This is the ceiling function. So n divided by k ceiling, where ceiling x equals the smallest integer greater than or equal to x.
Ceiling is rounding up, right?
Rounding up, yeah. Well, not rounding.
Well, like if it has a decimal, you go up.
You go up one, yes. So, sidebar. What's the smallest integer bigger than or equal to 2?
3 equals to 2.
Yeah, 2. Smallest integer bigger than or equal to 2.1, that's got to bring you up to 3. Smallest integer bigger than or equal to 2.99, that's also 3. And then ceiling 3, that'll be equal to 3. So if it's an integer, it's just an integer. If it's bigger than an integer, you round up. So for n objects in k boxes, at least one box has ceiling of n over k objects in it. So in the pigeonhole principle, we had k boxes and k plus 1 objects. K plus 1 over k, that's always 1 point something, it rounds up to 2. So we get the idea that we have a box with at least 2 objects. But if you have 22 people and 7 days of the week, and we make a box for each day of the week, ceiling of 22/7 is a ceiling of 3 point something. That's 4. So 22 people, at least 4 of them share the same birthday of the week. You want a weird one?
Yeah.
We'll wrap up with a weird one. So this is a theorem we can prove. Every positive integer has some multiple consisting of only zeros and ones. Pick any positive integer, you can find some multiple of that number that when you write it out in decimal, it's just a pattern of ones and zeros. So 5, for example, I can multiply by 20, and that's 1,000. There's my pattern of ones and
Just
zeros.
divide by 2.
2, and get 10.
Or I multiply by 2.
Always complicating things.
Yeah, I know. What about 7?
40, I think.
But
Seven.
that's not ones and zeros.
Oh, that's
Yeah, that's 280.
but we still got a 0 in there, so maybe we can climb up
40
that
times
way.
25 is 1,000.
Yeah. Try 7 times 143.
That's 1,001.
That's 1,001. And this works for any integer. You can always find a multiple that you can write as just a string of ones and zeros. How the heck do we prove that?
Pigeon Hole.
Pigeon-hole principle or magic.
Magic is the best.
Probably could do it with modular arithmetic.
Modular arithmetic will be our friend in this.
How did you find 143 so fast? What's the technique?
I know
Oh, I thought
things.
he said that. Yeah.
He deliberately chose 7 to mess with us.
Maybe. All right, think about that. We'll talk about it tomorrow. I'll let you out 2 minutes early so I have time to get to my office.
Oh,
Don't think about it too hard.
I'm just dealing with regular expressions, so.
Cool. All right, I'll see you later.
Oh.
Don't forget your camera.
That's what I was going to my office for, was to put my camera online.